When you type a web address and hit enter, your browser sends a carefully structured request to a remote server. Think of it as dropping a specific, well-crafted letter into the mail. Within milliseconds, the server processes that request and sends back a reply envelope that dictates exactly what your browser should do next. This diagram shows a basic HTTP response, and you can see it is cleanly divided into 3 distinct parts. At the top is the status line. Below that is a block of headers. Finally, separated by a distinct blank line, is the body. Looking closely at that top section, the status line acts as a quick summary of the outcome. A code like 200 tells the browser the request was a success. If the page doesn't exist, the server drops a 404 not found. A 403 means the server understands the request but forbids access, while a 500 indicates the server itself crashed while trying to process the request. These 3 sections work together to form a strict set of instructions. The specific codes and text within this layout determine what content you ultimately see and whether the server permits you to view it at all. Immediately below the status line are the headers. These act as metadata and synchronization instructions. Headers like server identify the software running on the backend, date provides a precise timestamp for caching, and content length tells your browser exactly how many bytes of data it needs to download before the page is complete. This split comparison shows why the content type header carries so much weight. Browsers do not inherently know what type of file they are receiving. If the server sends the header as text plain, the browser simply displays raw, unformatted code. But if that exact same data is sent with a text HTML header, the browser reads it as a web page and renders the formatting visually. This header also determines how the browser handles user-provided text that the server echoes back into the page. If the content type is text.html, the browser interprets that echoed text as instructions and runs any scripts it contains. However, if the header is text.plain, the browser treats the script as inert text, rendering it harmlessly on the screen. Because the browser trusts these instructions blindly, a single missing or misconfigured header can cause a page to break entirely or create a working exploit out of seemingly harmless text. Moving past the headers, there is always a mandatory blank line. That empty space is an explicit signal to the browser that the instruction phase is over and the actual content is about to begin. The content that follows is the response body. This usually consists of raw HTML, CSS, or JSON data. If you were to copy just this raw text, save it locally as an HTML file, and open it, your computer's browser would build and display the web page entirely offline. Web developers routinely read through this raw response body. By checking the exact code the server delivered, they can diagnose why a specific image failed to load, or pinpoint exactly where a style sheet link broke during the transfer. This raw HTML code features exactly the kind of target hackers look for. When inspecting the body, penetration testers hunt for text that the browser hides from the visual display. Developers often leave behind debug comments, accidentally expose API keys in JavaScript, or, as seen here, leave a direct link to an internal admin panel completely visible in the source code. The polished interface you interact with on your screen is heavily filtered. The raw response body delivered to the machine often contains sensitive back-end details that were never meant for public view. To catch these details, cybersecurity professionals use web proxies like Burp Suite. A proxy sits directly between the browser and the server, allowing an analyst to pause, read, and modify live traffic before it ever renders on a screen. Consider what happens when a user types a web address without specifying a secure connection. The browser sends an unencrypted HTTP request. By intercepting the server's immediate reply through a proxy, we can see exactly how the server handles the error. This flowchart demonstrates that interception. The server replies with a 301 moved permanently status code and includes a location header. This tells the browser to drop the current connection and instantly reroute to the secure HTTPS version of the site. Notice the content length header is set to 0. Because the server is issuing a redirect, there is no HTML to display and no body to send. It is saving bandwidth by issuing a purely structural command. Servers do not always need to deliver a visible page to dictate the user's experience. Using invisible headers, they can command the browser to drop connections, change paths, and enforce secure routing entirely in the background. Even in those empty redirect responses, headers provide data about the state of the backend. If a server returns a date header from 2018, it suggests the system is running highly outdated software that hasn't been updated or patched in years. These metadata timestamps help an analyst identify which servers are likely sitting on unpatched vulnerabilities. To counter this, administrators deploy defensive security headers. Directives like strict transport security force the browser to only use encrypted channels for future visits, while XSSS protection commands the browser's built-in filters to block known scripting attacks. Pause the video and take a look at this block of realistic HTTP response headers. Can you spot a custom header that might be leaking internal diagnostic intelligence to an attacker? If you spotted the Netflix header, you found it. Companies often inject custom headers to track how long a request takes to pass through their internal load balancers. While useful for their engineers, it hands external attackers a map of the back-end proxy infrastructure and processing times. An HTTP response is a balancing act. Every line of text sent back to the client either enforces a security boundary or reveals the technical logic of the internal network. This side-by-side chart illustrates the difference between proper configuration and a liability. The vulnerable response openly advertises outdated software and lacks headers to stop scripting exploits. Developers must strip out verbose banners, scrub the HTML for debug comments, and automatically attach strict security headers. Whether it is a blank redirect or a media-heavy homepage, the cycle remains the same. The status code declares the result. The headers dictate the browser's behavior, and the body delivers the raw code to be rendered. Thank you for watching. If you want to master more cybersecurity concepts, make sure to subscribe to This Will Surprise You. Let me know below which networking or security topic you want us to break down next.